Hello, everyone, and welcome back to our last lecture of statics, in which we are going to solve two problems of uh, belt friction, one on belt friction and one a combination of belt and drive friction. Last time, we derived the equation between the two tensions in a drum when it's rotating either clockwise or counterclockwise. I'm usually I taught this course like years, and we always assume T2 is larger than T1. But when I copied that from an online site, they had the T1 was bigger. So I hope this doesn't confuse you. Just think which one is the bigger, and it equals the other times e to the mu sub s times theta or beta, I'm sorry. So that's another problem here. So here we have a motor attached to the uh, to point B, the shaft here, and this thing rotates. It doesn't matter which direction here. Why? Because if it rotates clockwise, then this would be the higher tension, which we call T1, but I call T2, and this would be the lower. If it rotates in the opposite direction, that would be the higher, that would be the lower, but the magnitude would be the same. So it really doesn't matter here to say in which direction uh, they the pulleys rotate. But what's important here, they tell you that the maximum tension that these cables can, or these belts can withhold, maximum tension is 450 Newton. Okay. And then mu sub S between the pulleys and the belt is zero point 0.4. That's a high enough. Oh, by the way, remember we said I have to write a T1 instead of T2. I don't like it because it keeps, I keep thinking the other way. If you notice, maybe if you look in the engine of your vehicle or something, or some machines, you will see that these, we are not using flat belts. There is a better way to do it, is that if you take a cross section of the belt, the flat belt, it's rectangle like that. But we have other belts that have an angle, so they look something like that. I'm going to exaggerate and make it bigger. And if you join and complete the letter V, you will get an angle alpha here. These belts can withstand higher tension. Basically, they can develop higher torque, so to speak. Here, when we say T1 equals T2, I hate to say it, but it's T2 equals T1. It doesn't matter. The higher equals the lower times e to the mu sub s times beta. For these types of belts, T1 equals T2 e to the mu sub s enhanced times beta. There is an enhanced uh, like uh, coefficient of static friction because it's and mu sub s enhanced equals mu sub s divided by sine of alpha over 2. So it tells you this is a 10-degree belt or 18 degrees belt. They give you the alpha. And you can see that the sine value is less than 1, right? And the smaller the angle, the smaller the value of sine alpha over 2. So when you divide by a small number, it increases mu sub s. And when you put it as an exponent to e, that even makes it much larger. This problem doesn't have to do with enhanced belts, but I just remember that we never mentioned that. As I said, you most likely will see it in any textbook. I don't know, I should have noticed before, uh, like before taping the video and uploading it, that it had it backwards. I just noticed that while I was doing the session. But that's basically how we refer to T1 as the smaller, T2 as the bigger. But as I said, as long as you know what you're doing, it really doesn't matter the nomenclatures. But this is the way usually in engineering we use. So we use when you hear T2, it's the higher. But if you are doing the math, it really doesn't matter, as I said. Okay, so they want to see, of course, this small pulley attached to the motor rotates, but you see why the belts get wider and wider because you know the torque equals the tension times the radius. So that's why we use a larger radius for this fan or whatever you are using the motor to drive. So you can use a small torque here, but then you are delivering higher torque. We want to know if the tension, maximum tension in the belt is 450 Newton, what is the largest or what would be the value of the torque that it produces? So here, all what you have to do is to start writing this equation. This is a very simple problem. Since I use T1, I'm going to say T1 equals T2. Notice I have to make T1 or the bigger one 450 because if I make the smaller one 450, the bigger will snap. It can't withhold. So this is can be rewritten when let's write the equation first, like we always do. We are going to say 450 equals T2 times e to the 0.4, and then we need to find, excuse me, we need to find the angle. Notice the point here and the point there. How do you find this angle? You have to be careful here because this we will use that at the end, but in the beginning, I'm turning the cable here. So that is beta that we are using, not that. In other words, the motor is connected to pulley B. That's what it rotates. So that what generates the torque, and that's where I'm going to use, that's what I'm going to use to find T2. So you have to look at the bottom or the smaller pulley, not the bigger pulley. That's very important because if this angle, of course, this is 15 degrees, 15 and 15, 15 and 15. So that is 180 minus 15 and 15. Because if this angle is 15 and this angle is 15, I'm doing 180, which is this guy, minus 15 from here, minus 15 from there. So it's 150 degrees. Of course, here it would be 210, but I'm not generating the torque here. I'm generating it here, and then I'm delivering it to the big one. So that you always work where the motor is. So this would be 150. 150 meaning 5 pi over 6, right? Again, you can multiply by pi, divide by 180, simplify by 30 degrees. So that becomes 5, and that becomes 6. So 5 pi over 6. Meaning, to find T2, I will be dividing 450 divided by e raised to the power of 0.4 times 5 pi over 6. It's 157 or roughly 158 Newton. So the bigger is 450. Doesn't matter which one because it can be rotating clockwise or counterclockwise. But when you go to the big pulley, the torque here is the bigger force times the radius minus the smaller force times the radius. So the torque here, the maximum torque delivered would be, in this case, 450 minus 158 times the radius, which is 0.12 meter, because that's 120 millimeter. So we'll do 450 minus 158 times 0.12, we said, and you get 3505, 35.05 Newton meter. Okay, so that's how we solve a problem like that. Very pretty much similar, most of them. But then now we come to the last problem I wanted to work with you. Where did I place it? Oh my God. Oh, I think it's this one. Nope. Oh, here it is. I found it. Should have placed it nearby. Um, Again, I can't remember the mu sub s, but we can say, let's say mu sub s between these two is, what is going on? 0.25, and between this part and the cable, so we're no longer going to assume it's smooth, right? It's smooth here for this pulley, but here it is, let's make it 0.35 or 0.3. And let's make both of these the same, like 0.25 and 0.25. Okay, so now what we are saying is, if these are mu sub s's, what is the smallest force you need to use to initiate motion of the blocks? You will notice here that they give you the dimensions of the top block. Why is that? They made it slender, right? And they want you to check which tension, how much tension would produce tipping, how much tension will produce slipping, and then which one will you use? The higher or the lower? No, not the higher. Some said the higher. No, it's the lower. Why? Because you would reach it first. Suppose you need just any numbers, 50 Newton to tip it over and 70 to move it. So you apply a force of 10, 20, 30, 40, 50, it will tip over. So you will never reach the 70. So always it's the minimum, right? So let's calculate T required. So let's say T required for slipping. Let's call this A and this is B. Slipping block A. Or we could have said the 100 Newton block. Okay, so in order to do that, we will draw the free body diagram of the block. Again, we don't want to waste time on that. Just any rectangle, I don't care about it. For slipping, we don't even need the dimensions, so I'm not going to show anything. All what I'm going to say is there is a tension here. There is a weight here of 100 Newton, and there is friction, A sub F and A sub N. And this is very simple, since I can find the normal force very easily, right? I can say summation of the forces in the y direction equals 0, up is positive. I have A sub n minus 100 equals 0. So A sub n equals 100 Newton going up. We know that A sub f equals, we said it's 0.25, 0.25 A sub n equals 25 Newton to the right. Sum of the forces in the x equals 0, right is positive. I get 25 minus T equals 0, so T equals 25 Newton to the left. So a tension of 25 Newton will slide this block. Now, let's do T required for tipping. Okay, so quickly we are going to draw another rectangle. And here you don't need to show X and Y. Okay. Remember, like 3 sessions ago when we introduced the dry friction, I told you, okay, I told you at the time something important. I told you to think of any force applied to a block that it is pulling the normal force with it. So if that's a T, the weight doesn't change, it's still here, 100 Newton. But at the point of impending tipping, A sub n reaches the edge. And I have A sub f, of course. So what happens when it reaches the edge? This force and that force intersect here. So let's call this point O. And if I take the moment about O, I can find the tension because I have the dimensions, right? It's 0.5 and 2.5. 0.5 here and 2.5 meter there. So now what you need to do is to say summation of the moment about O equals 0, counterclockwise is positive. The tension is rotating counterclockwise, so 2.5 tension minus the 100 going clockwise, and the half the distance is 0.6, right? The weight is in the middle. So minus 100 times 0.6 equals 0. And then I solve, so I get T equals 60 divided by 2.5 equals 24. Oh my God, I should have picked a different number here. This is funny. 24 Newton. 24 is less than 25, so this thing would be about to tip before it slips. Okay, so I cannot exceed 24. So, because I picked 24, I'm going to use this value. What does that mean? It means that A sub f from the summation, and now maybe I need to show my X and Y. I thought the other one, anyway, I thought this would be smaller, but apparently A sub f equals, or A sub f uh, minus the tension, which is 24, equals 0. So A sub f equals 24 Newton to the right. Someone say, why do you do it? Because if not, I would have used A sub f as 25 Newton, while in fact it's only 24. Well, there is no big difference between 24 and 25. Probably it was a bad choice of mu sub s from my point of view. Probably this was higher in the original problem, maybe 0.4 or something. So at least you get 40, and then you would say this is smaller, so you take that. In this case, it really doesn't matter. They are almost identical. But theoretically speaking, you have to say AF is 24, not 25. But what are you going to do after that? After that, you say, okay, this tension is 24. It stays 24 because this is a smooth pulley. No loss of tension here. Okay? Up until it comes here. So you have to say, we don't want to use more than one page. So I'm going to say free body diagram of the drum or this fixed drum. Okay. So Again, I'm not going to waste time. I'm going to draw what looks like a circle, but it's not. And I say this tension is 24 Newton. It makes an angle of 30 degrees with the horizontal. And this tension is different. Okay? But is that T1 or T2? Oh, the higher or the lower. Forget about T1 and T2. I'm really sorry. I should have reversed them and make T2 is the bigger. But again, if you are pulling here, which tension do you think would be higher, the horizontal or the inclined? Okay. If it's not like a drum, even in drum you can do it, but even if it's not in a drum, think about the higher tension is always with the direction of motion. Okay. Meaning, if I pull, this thing would go down. You see the arrow is going up, but the motion is down. They are opposite to each other, so that is the lower. And the tension follows the arrow, that's the higher. We call that T2, but according to what I did last time, I would say T1, but I would say T, just T, because the other one is 24. I'm sorry. And then we say, okay, so T equals 24 times E raised to the power of 0.3 beta. What is beta? The angle in radian. As I said, I had many students having trouble with that, even though I think it's so easy the way I present it. I don't know, maybe I just think that and it's not easy. All what I said is you bring the cable, okay? Just the cable. You lay it like it's like on this T. And then I'm going to turn it 90 degrees and another 30 degrees. I'm done. So I turn it 90 and 30. That's 120. Why is that hard? I don't know. But or you can say, okay, here is this radius and that radius, and what is this angle? Again, it's 30 plus 90. 30 plus 90 meaning 120, and 120 meaning 2 pi over 3. So times 2 pi over 3 equals, and then use your calculator. This is 0.2 pi, since 3 and 3 cancel. So you can say 24 raised to the power of 0.2 pi. Get 44.45 Newton. So now the tension here is 45 Newton. And finally, you are going to draw the free body diagram of the bottom block of the block B, which is the 200 Newton. Free body diagram of block B. So now I have a rectangle, which is the bottom block. There is a tension. Tension always goes out of the object. And this tension is 45 Newton and 44.98. We're going to use 45. Now, be careful here. I'm going to take the 100 Newton, which didn't change here. I don't care about it. And I invert it down. So here there is 100 Newton. And A sub F was 24 to the right, so I have 24 to the left. I have the weight of the block, which is 200 Newton. And then I have B sub N going up. and B sub F going to the left because I'm going to pull to the right. And both frictions oppose the motion. And then I have P. Here is my X. Here is my Y. And that's a special case. Remember when I told you the normal force equals the weight if and only if two things are satisfied. The blocks are resting on horizontal surface. The B is on horizontal, the A is horizontal. And all the outside forces acting on the blocks are horizontal. This cable is horizontal, this cable is horizontal, and you are applying a horizontal force. So that's the only time my B sub n would be 300. I don't need to do any math. I know the weight of the blocks is 100 and 200, so Bn is 300. But it is not always true. If I make any one of these cables or even this force slightly not horizontal, I change the angle, then the normal force will not be 300. So please don't take that, you know, wrong idea that normal force is exactly the weight, but opposite direction. That's a nonsense. Okay. We start with the summation of the forces in the y or the x. No, the y, of course, because in the x I have two unknowns. Okay, so I have to do the y first and then use b sub f equals mu sub s times b sub n. Sum of the forces in the y equals 0. Up is positive. I'm going to say, this is easy. I'm going to say b sub n minus, so instead of saying minus, I say equals 100 plus 200. That's the only two forces that are vertical. And then I say b sub f equals mu sub s times b sub n also equals, I'm sorry, times 300 equals 75 Newton to the left. And finally, to solve the problem, I say sum of the forces in the x equals 0. Right is positive. I have P. That's what I want. So I'm going to say equals, and everything else is to the left. So I have 45, I have 24, and I have 75. So these are 120, 144 Newton. That's the force that you can apply to initiate not motion, but you reach the point of impending, in this case, impending tipping. And it would be impending motion also, but you know, once you move, the top block would fall down and probably be smashed. So maybe you decrease this 0.25, make it 0.2, in which case it will start sliding before tipping over, and you get smaller tension that you can apply. Anyway, I think this one combines everything. So we have dry friction, we have tipping versus slipping, and we have belt friction. And this one is no friction because it's a smooth pulley. Okay, so that concludes really the course of statics that we usually take in college. I will start thinking about other stuff that may be mathematical or engineering that we can introduce soon. And until then, I hope you have a great time and hope to see you soon.